You usually expect a pretty comforting degree of permanence in engineering and construction.
Right. You want things to stay put.
Exactly. I mean, you calculate the load-bearing capacity of a steel beam, you pour a concrete foundation, and you just know exactly how it's going to behave.
It's precise, predictable.
It is. But today, you are stepping into a totally different world for this deep dive. We are talking about gynecological soft tissue engineering.
Which is basically a biological earthquake zone.
That is the perfect way to put it. You're taking a static engineered filler and putting it into an area, specifically the labia majora and the anterior vaginal wall, that is highly dynamic.
Yeah, it's subjected to constant friction, stretching, physical compression.
So our mission today is to figure out, how do you engineer a hyaluronic acid gel to actually survive and, integrate into that chaotic environment?
It's a massive challenge. You are trying to build lasting structure in an ecosystem that is evolutionarily designed to break foreign materials down. So to even approach a solution for loose labial subcutaneous tissue, we really have to look past the marketing brochures and dive straight into the physical chemistry.
The actual science of it.
Specifically, we need to look at the molecular weight distribution of these hydrogels.
And to really grasp that, we first need to understand the paradox of hyaluronic acid, or HA, itself. Because before a lab ever touches it, HA is basically a biological shapeshifter.
It really is.
Let's unpack this. What exactly is HA when it's just doing its normal job inside your body?
Well, in its purest physiological form, HA is a naturally occurring biopolymer. Specifically, it belongs to a class of molecules called glycosaminoglycans.
Okay, let's pause there for a second. Glycosaminoglycan is a really heavy piece of jargon.
It's a mouthful. Yeah.
Essentially, we're just talking about a very long, unbranched chain of repeating sugar molecules, right? Like just a massive string of disaccharides.
That captures it perfectly.
Yeah.
It's a long, simple sugar chain. But its defining characteristic, the reason it is absolutely vital to human biology, is its astonishing hygroscopic capacity.
Meaning its ability to hold water.
Exactly. A single molecule of HA can hold up to 1,000 times its own weight in water.
1,000 times. That's insane. It acts like a microscopic sponge with a nearly infinite capacity.
Right, and that water binding ability is what generates osmotic pressure in our tissues. It's what gives skin its bounce, its viscoelasticity.
It provides that hydration, but this HA doesn't just, float in from nowhere. Our cells actually manufacture it on demand.
They manufacture it continuously, actually. The process happens directly at the inner plasma membrane of our cells, driven by 3 specific enzymes.
Okay, what are those?
Hyaluronin synthase 1, 2, and 3, or, HAS1, HAS2, and HAS3. You can picture these enzymes as biological extruders.
Like a machine pushing out material.
Yeah, they sit right at the cell membrane, actively stringing those sugar units together one by one, and then pushing the growing polymer chain out into the extracellular matrix.
Wow,
But the critical variable here, and this is foundational to everything we'll discuss today, is that these different enzymes produce HA chains of entirely different lengths.
So they aren't all uniform.
Not at all. And the
Oh.
physical size, or the molecular weight, of that chain completely dictates how it behaves biologically.
Right, and this is the whole Jekyll and Hyde dynamic we see constantly referenced in the research. Depending on its weight, HA behaves like 2 completely different entities.
Exactly.
Let's look at the Jekyll side first. High molecular weight HA, or H&W HA. We're talking massive chains here, usually in the range of 2 to 6 megadaltons.
And at that colossal size, HMWHA acts as a biological peacemaker. It is profoundly anti-inflammatory.
It's because it's just so physically large.
Yeah, because the chain is so massive, it actually folds over on itself, forming this dense, entangled polymer network.
Okay.
This network provides intense structural hydration, but it also physically shields the tissue. For example, it prevents macrophage-mediated phagocytosis.
Wait, macrophage-mediated phagocytosis? So it essentially stops the body's cellular Pac-Men, the macrophages, from attacking and engulfing the surrounding tissue cells.
You nailed it. It creates a literal physical and chemical barrier that prevents those immune cells from binding and causing damage.
That's fascinating.
It suppresses unwanted cell proliferation, keeps the tissue cushioned, and really just maintains a quiet, healthy equilibrium.
But then you have the Hyde side, right? Low molecular weight HA, or LMW HA.
Right, the troublemaker.
These are the tiny fragmented chains, anything under 10 kilodaltons. The sources describe this as a blaring biological alarm bell. But I really want to understand the mechanism here. How does simply being a smaller piece of sugar suddenly make it pro-inflammatory?
Well, it all comes down to receptor binding. A massive 4 megadalton HA chain is simply too large to bind to certain immune receptors on our
It
cells.
just physically blocks them instead.
Exactly. But when that massive chain is chopped up into tiny 10 kilodalton fragments, those small pieces are the exact right size and shape to bind directly to toll-like receptors on the surface of your immune cells.
Oh, so they fit like a key in a lock.
Yes, and when those fragments plug into the receptor, they flip a genetic switch. They activate immune responses, promote cell mobility, and basically signal to the surrounding tissue that damage has occurred.
So it's telling the body an emergency remodeling response is required.
Precisely.
So, if HMWHA is like the sturdy steel frame of a building, providing shelter and structure, LMWHA is the rapid response emergency crew swinging wrecking balls because they assume the building is actively collapsing.
That is a brilliant analogy. The heavy polymer builds and protects, while the light fragment binds to receptors and initiates frantic inflammation.
Which, raises a really obvious question for anyone looking at soft tissue augmentation.
I think I know where you're going with this.
If natural high molecular weight HA is this perfect, hydrating, anti-inflammatory peacemaker, why can't we just extract it, put it in a syringe, and inject it directly into the labia to restore volume?
Right, why bother with the lab?
Yeah. Why go through the incredibly complex, expensive engineering process to create a synthetic filler if the body already makes the perfect material?
Because if you injected pure, unmodified HMWHA into the human body, it would vanish before it could provide any meaningful structural support.
Why is that?
Our bodies are just saturated with naturally occurring enzymes called hyaluronidases, and their entire evolutionary purpose is to hunt down and cleave HA chains.
Oh, wow.
So an injection of natural HA would be aggressively broken down, metabolized, and cleared out in a matter of days. It has zero long-term structural durability.
It's just completely biodegradable on a hyper-accelerated timeline.
Exactly.
Which means to use it medically, we have to find a way to armor this peacemaker so it can survive a highly hostile environment. How do scientists actually engineer that armor?
They utilize chemical cross-linking technologies. The manufacturing process introduces chemical agents, the most common one being BDDE.
Which stands for 1,4,4-butynedyl diglycidyl ether, right?
That's the one.
Let's visualize that mechanism for a second. If natural HA chains are, say, like loose strands of cooked spaghetti sliding freely past one another in a bowl,
I like that.
a cross-linker like BDDE acts like molecular zip ties, permanently tying those strands together at specific intersection points.
Yes, it creates strong covalent bonds between the chains. So it converts a fast-degrading viscous liquid into a robust, three-dimensional mesh.
And we call this a viscoelastic hydrogel.
Correct. And here is how that specific process protects against those degrading enzymes. By tying the chains into a tight, complex web, you are physically hiding the specific molecular bonds that the hyaluronidase enzymes want to cut.
Oh, so the enzymes can't even get to them.
Right, they physically cannot access the cleavage sites because the 3D mesh is too dense and entangled. We call this steric hindrance.
Steric hindrance. And that allows the filler to persist in the tissue for months, sometimes years.
Exactly.
But once you tie those chains together and create that tight web, you fundamentally change the physical properties of the material.
You completely alter how it behaves, yeah.
This brings us into the realm of rheology, the physics of how materials flow, deform, and respond to stress. We have to figure out how this newly formed hydrogel is going to behave when it's finally inside a patient.
Right, and when evaluating these gels clinically, we look at several dynamic parameters. One of the most critical is the elastic modulus.
Denoted in physics as G prime.
Yes, G prime. It represents the gel's firmness, its stiffness, and its ability to store energy and resist deformation.
So a high G prime means a very firm gel.
Exactly. It has strong lifting capacity. If a clinician is trying to simulate bone, like building a jawline, they require a high G prime gel to hold that sharp shape against the skin.
But wait, the jawbone is static. It provides a rigid, hard backboard for that stiff gel to rest against. Injecting a firm, high G prime gel into the highly elastic, loose, dynamic tissue of the labia would be a total disaster.
It would be awful. It would feel like a hard pebble in an area that is constantly shifting.
So you have to balance that firmness with complex viscosity and cohesiveness. I always use the ketchup analogy to explain viscosity in these materials.
Getcha. Okay, let's hear it.
It needs shear thinning behavior.
Yeah.
Like when a clinician applies high pressure to the syringe plunger, that high shear force momentarily aligns the polymer chains, making the gel thin and fluid so it passes smoothly through a tiny fine gauge needle.
Yes, and the split second that pressure ceases, the gel must instantly recover its 3D structure,
Right. It cannot continue to flow like water, or it would migrate away from the injection site.
which would be bad. But even more critical for soft tissue integration is the gel's cohesiveness. Cohesiveness is a measure of the internal stickiness of the gel.
Like the inherent affinity the cross-linked HA particles have for one another. If it lacks cohesiveness, doesn't it simply fracture under pressure and diffuse randomly through the tissue planes?
Yes, it won't hold a unified, predictable shape. A highly cohesive gel, on the other hand, integrates homogeneously into the tissue matrix.
It moves as a single flexible unit rather than breaking apart when the patient moves.
You got it.
And this brings us right to the core engineering problem of our deep dive. We are targeting gynecological aesthetics, specifically the labia majora and the anterior vaginal wall.
A very tricky area.
This tissue is incredibly loose, highly vascular, and subjected to massive amounts of shear stress and physical compression. So how do you formulate a gel that is cohesive enough to stay put, firm enough to provide volume, but flexible enough to integrate smoothly into that specific environment?
Well, the clinical data and rheological studies provided in the sources point to a surprisingly exact target for this anatomical region.
Really? What is it?
The ideal integration happens with the cross-linked HA gel mixed at exactly 2 megadaltons and 1 megadalton, suspended in a 25 milligram per milliliter concentration.
Okay, I have to challenge this point.
Go for it.
We established earlier that 2 megadaltons provides the structural backbone, like the durability and hydration needed to resist physical compression.
Right.
And 1 megadalton is smaller, giving the gel flexibility and moldability so it doesn't feel rigid.
Yes.
But why go through the complex process of blending 2 completely distinct molecular weights? Why not just engineer a uniform batch of HA at, say, 1.5 megadaltons?
That's a very common question.
Wouldn't finding that mathematical middle ground give you the best of both worlds in a much simpler formulation?
It's a very logical assumption.
Yeah.
It's something material scientists heavily explored.
Hmm.
But the physical chemistry proves otherwise.
Really?
Yeah, a uniform 1.5 megadalton gel simply does not yield the necessary rheological properties for loose tissue.
Interesting. Why not?
By mixing a bimodal distribution, specifically the distinct 2 MDA and 1 MDA chains, you create a much more complex interlocking entanglement within the 3D mesh.
Ah, so they interact differently.
Exactly. The shorter 1 MDA chains essentially weave between the larger, stiffer 2 MDA structural pillars. They act almost like internal lubricants and binding agents.
So it's not just an average of the two?
No, this bimodal matrix creates a superior shear thinning profile for injection and a significantly higher cohesiveness than a uniform 1.5 MDA gel could ever achieve. The contrast in chain lengths is what creates the optimal physical behavior.
The chains literally lock together better because they are different sizes.
Yes.
That makes sense. It creates a dynamic flexibility that a uniform size just can't replicate. It allows the filler to absorb the mechanical stress of the labia without fracturing while still maintaining enough structural integrity to provide the desired volume.
And the engineering of this specific formulation goes even further.
Oh.
The studies mandate that this bimodal matrix must have minimal residual crosslinker. Specifically, unreacted BDDE must be kept below 0.1 parts per million.
Which makes perfect sense when you think about the biology. I mean, BDDE is a harsh reactive chemical.
Very harsh.
You want it doing its job forming covalent bonds to tie the chains together, but you absolutely do not want free-floating, unreacted chemical sitting in highly sensitive mucosal or labial tissue.
Definitely not. That would trigger a massive inflammatory response. Keeping it below 0.1 ppm ensures strict biocompatibility.
And what happens when it's placed safely?
Well, when this precise 1 and 2 MDA mixture is utilized safely, animal models show it doesn't just sit inertly in the tissue acting as a passive space filler.
It does more than just take up space.
It actively promotes local tissue remodeling. It encourages neoangiogenesis, which is the formation of new blood vessels, and promotes cellular regeneration around the gel, completely without any evidence of distant migration.
The gel stays exactly where it is placed and becomes part of the living tissue.
It really does.
I also noticed a fascinating detail in the clinical data. Some of the most advanced specialized formulations for this niche are adding amino acids directly into this 1 and 2 MDHA matrix, specifically glycine and L-proline.
Yes, that's a newer advancement.
Now, I know those two amino acids are the fundamental building blocks of collagen in our connective tissues. But why embed them inside a hyaluronic acid filler? Are we, like, trying to trick the body into building its own structure?
In a biological sense, yes.
Oh.
By saturating the HA hydrogel with glycine and L-proline, you are providing the surrounding fibroblasts, the cells responsible for making connective tissue, with the exact raw materials they need to synthesize new native collagen.
So it's feeding the cells.
Exactly. As the filler slowly integrates and eventually begins to degrade, it provides a stable scaffold, and those embedded amino acids actively support the cellular regeneration of the host's own connective tissue.
That would significantly enhance the overall durability of the aesthetic result, wouldn't it?
It absolutely does.
This is truly brilliant chemical engineering. So we have a bimodal 1 and 2 MDA distribution for optimal structural flexibility, a 25 milligram per milliliter concentration for volume, sub 0.1 ppm BDDE for absolute safety, and amino acids to jumpstart natural collagen production.
That's the recipe.
So, if you are a patient or a clinician mapping this out, does this mean you can just look at a product label, confirm these exact specifications, and guarantee a perfect, highly predictable, long-lasting result every single time?
Well, here's where we hit the absolute biological wall.
I had a feeling.
The clinical FAQs from the Women's Health Clinic sources issue a stark reality check.
Yeah?
Chemistry does not happen in a vacuum.
Right.
The molecular weight distribution will strictly dictate the gel's baseline physics inside the syringe. It tells you the G' and the cohesiveness.
But once it's injected,
It absolutely cannot be used as a direct predictor of patient-level duration, integration speed, or subjective sexual response.
because the chemical blueprint is flawless, but the biological construction site is, well, utterly chaotic.
The body always casts the final deciding vote. The anterior vaginal wall and the labia represent a profoundly dynamic ecosystem.
So many variables.
So many. The actual longevity of that perfectly engineered filler is entirely subjected to the host's unique physiological environment. We're talking about constant, localized variations in tissue pH.
A lower pH, like a more acidic local environment, could accelerate the degradation of those polymer bonds, regardless of how well they are cross-linked.
Absolutely. Furthermore, you have to account for fluctuations in localized body temperature, the baseline level of systemic or local inflammation in that specific patient, the extreme shear stress placed on the area through daily movement.
And let me guess, the localized concentration and aggressive activity of the patient's own hyaluronidase enzymes.
That is the biggest factor, yes.
So you could take two different patients, inject the exact same perfectly engineered 1 and 2 MDA gel into both, and it might last a full 14 months in one person, but completely degrade in just 6 months in the other, simply because the second patient has a higher baseline of naturally occurring enzymes or localized inflammation.
That is a very common clinical reality, unfortunately. And it highlights an incredibly important caveat for practice. The sources strongly advise against patients engaging in product shopping based merely on reading isolated chemistry terms like molecular weight or cross-linking density on a clinic's website.
Because seeing those numbers creates a false sense of mathematical certainty. You think you are buying a fixed math equation, but you are actually initiating a highly unpredictable biological dialogue.
A profoundly complex dialogue.
Right.
Understanding the 1 to 2 MDA requirement is vital because it proves the gel has the necessary biomechanical properties to exist safely in loose tissue without migrating or forming hard nodules.
The foundation has to be right.
Yes. But the ultimate clinical success of the procedure relies heavily on practitioner technique, the precise depth of placement in the subcutaneous layer, baseline tissue health, and just the unpredictable variables of human biology. The chemistry is really only half the equation.
It really is a humbling intersection of material science and human biology.
It truly is.
If you are analyzing this for a clinical application, or if you're just fascinated by the engineering, the core takeaway is pretty clear.
Let's summarize it.
We start with natural HA, a massive hydrating peacemaker that is aggressively hunted and destroyed by the body's own enzymes. We armor it with chemical crosslinkers like BDDE, hiding its vulnerable bonds to create a durable, viscoelastic hydrogel.
Right.
And when targeting the intense, dynamic, high-friction environment of loose labial tissue, the engineering sweet spot is a bimodal mix of 1 megadalton and 2 megadalton HA.
Because of the weaving effect.
Exactly. This specific combination weaves together to provide both the structural resilience to withstand compression and the shear thinning flexibility needed to integrate smoothly without feeling like a foreign object.
Spot on.
But ultimately, all of this perfect physics is completely at the mercy of your own enzymatic and inflammatory microenvironment.
The environment always dictates the final rule.
Always.
And, drawn directly from the biological mechanisms we've explored today, there's a final, rather profound question worth considering before we wrap up.
Oh, here's where it gets really interesting. What are you thinking?
Well, we established that fillers are purposefully constructed using high molecular weight HA because of its anti-inflammatory tissue calming properties.
The peacemaker.
But despite the clever cross-linking, the body's hyaluronidases do eventually win. They slowly chip away at the gel over a period of months or years, cleaving those long sugar chains.
To break it down.
We also established that when HA is fragmented into tiny pieces, under 10 kilodaltons, it binds to toll-like receptors on immune cells and becomes a highly pro-inflammatory distress signal.
Oh, wow. Wait, I see the paradox here.
The question remains, as an intimate filler eventually degrades in the body, slowly breaking down into millions of tiny, low molecular weight fragments over the years, could the very mechanical act of its degradation trigger a localized biological shift?
That is, wow.
Could a material implanted specifically to be a peaceful anti-inflammatory structural support slowly transform, through the mechanics of its own inevitable death, into a localized pro-inflammatory trigger?
That is a wild biological concept to ponder. You install a peacemaker, but as it ages and fragments, it inherently becomes an alarm bell.
Exactly.
It's a brilliant reminder that when you intervene in human biology, there are no static events. Everything is a continuous, evolving process.
Never static.
Well, thank you so much for joining us on this depth dive into the source material. It just goes to show you that underneath the surface of everyday medical aesthetics is an entire universe of breathtaking physical chemistry and cellular biology. Keep questioning the science, keep looking beneath the surface, and we will catch you next time.